So after all of our hard work for the past few lectures, we can finally look at one of Maxwell's equations. So the first Maxwell's equation that we're going to look at is Gauss's law. And Gauss's law has everything to do with electric flux. We haven't talked about electric flux yet, so that's the first thing we should probably go through, which is what this video is about. But think of the electric field lines that we learned about in the last few lectures. So there are a bunch of lines, and electric flux would be a good measurement of how many of those lines pass through a certain area. So if you have a sheet of paper, for example, that's in an electric field, the number of electric field lines that pass through that paper or that imaginary surface would be can be quantified in terms of electric flux. So we'll go through a detailed overview of what this flux is in this video. And if you have any questions, be sure to reach out so that we can answer them. So to start off, we want to first define electric flux. And electric flux, given by the symbol capital Phi, is going to allow us to relate electric fields to their sources. Basically, we want to figure out how many electric field lines penetrate a surface. So we can then define electric flux as a measure of how many electric field lines pass through a given area. So there are essentially three different options. Essentially there's one general option, but I'm going to go through three possibilities. In order to measure the electric flux, we have to see how many electric field lines penetrate a surface. So let's assume the electric field is going this way. So we have our electric field in red, and we have our surface. With this surface, we also want to mention that there's going to be a vector that's normal to the surface. We call this n hat for the surface normal vector. So continuing on, let's use the exact same electric field. So the electric field is going towards the right, and our sheet of paper is laying flat along the electric field lines. So in this case, the surface normal vector is still going to be perpendicular to the surface and also perpendicular to the electric field line. So those are two different ways that we can rearrange our sheet so that the electric fields are penetrating the surface straight on, or the electric field is just passing through on the top and bottom. So in the general case, there's going to be a sheet of paper or a surface. It's going to be on a slant. So we're going to use the exact same electric field going towards the right. So electric field in red. But now our surface normal vector goes this way. And when we take a look more closely, that surface normal vector is going to be at an angle theta to the electric field. So in terms of these three cases, this one is when the electric field is parallel to the surface normal vector. This is when the electric field is perpendicular to the surface normal vector. And this is when the electric field is at an angle theta to the surface normal vector. So when we talk about electric flux, we want to be able to measure how many electric field lines pass through a given area. So looking at this option here on the left, we have maximum flux. Because all of the electric field lines are penetrating the surface straight on. In this case, the second one here, when the electric field is perpendicular to the surface normal vector, none of the electric field lines pass through the surface. There's no penetration, so there's going to be minimum flux. And then when the electric field is at an angle theta to n, there is going to be a component of the electric field that penetrates the surface at exactly 90 degrees. So we're looking for the component of the electric field along the surface normal vector, so there will be some flux. So some of the electric field lines are going to pass straight through the surface along the surface normal vector. So just from these explanations, when the angle theta is equal to 0 degrees, we get maximum flux. When the angle theta is equal to 90 degrees, we get minimum flux. And the proper vector multiplication that gives us that is the dot product. So therefore, the dot product of E dotted with N will give us electric flux. So then we can rewrite the electric flux equation. So we have electric flux is equal to E dotted with N hat, which is equal to E N hat cos theta. But in our case, we want something more relevant and something more convenient for us. So, but we want to give meaning to this surface normal vector. So we use ds in the n direction instead. And what this basically means is we have an electric field and it's going to pass through a surface. So then we have a small piece of surface, ds, differential surface element, and that vector is going to be pointing in the normal direction to the surface. So then we have, in order to calculate the total flux, we need to find the differential flux, which is equal to E dotted with ds, and then we have E ds cos theta. This is the equation for a differential electric flux. So if we integrate this differential electric flux, it's going to give us the total electric flux. So then integrating gives us total flux. And we get phi E is equal to the integral, or the surface integral, of E dotted with ds. And in some cases, we may want to use electric flux density through a displacement vector d. And we're going to define this as d equals to epsilon naught E. And if that's the case, then we can rewrite our electric flux equation and simply have the integral of d dotted with ds, and that is equal to epsilon naught E dotted with ds. So we're going to take a look at that later on once we introduce materials, and that will come in quite handy.